At the microscopic scale, the objects around us reveal a level of activity that isn't visible to the naked eye. What looks like still, solid matter is actually a landscape of moving parts. For over a century, scientists relied on Dalton's model, which defined the atom as the ultimate building block of the physical world. In this view, the atom was a featureless, unbreakable sphere. This view changed when researchers identified the electron. They found that these tiny, negatively charged particles lived inside the atom, proving that the indivisible sphere could be broken down into even smaller components. This discovery introduced a specific problem. If an atom contains only negative electrons, physics dictates those particles should repel one another with enough force to scatter. Without an opposing force to bind them, the repulsion between electrons would result in the atom scattering, making the existence of stable matter impossible. The electron was only one part of the story. Its discovery forced physicists to search for a hidden positive force that provided the structural tension necessary to keep the atom from flying apart. In late 19th century laboratories, researchers began investigating these forces using glass tubes and high-voltage electrical currents. The experiments involved filling these sealed tubes with gas at low pressure and observing how electricity behaved as it passed through the vacuum. Scientists noticed a distinct stream of rays that behaved differently than electrons. While electrons moved toward the positive end of the tube, these rays passed through a hole in the equipment and traveled in the opposite direction. Because they moved away from the positive electrode, these canal rays carried a positive charge. A key difference emerged. While electrons are identical across all elements, the mass of these rays changed depending on which gas was inside the tube. This suggested the positive particles were coming from the gas atoms themselves. By testing hydrogen, the lightest gas, scientists isolated the smallest unit of positive charge. They named this foundational particle the proton. The proton provided the necessary electrical balance. With both positive and negative components identified, the atom finally had a mechanism for electrical stability. However, even with the discovery of the proton, the sum of the parts did not match the total mass of the atom. The combined weight of protons and electrons only accounted for a fraction of an atom's actual mass. A significant portion of the atom's substance remained unidentified. In 1932, physicist James Chadwick conducted an experiment to identify this missing component. Chadwick directed a beam of alpha particles into a thin sheet of beryllium metal. The collision caused the beryllium to emit an unusual radiation that was previously unobserved. This radiation had the mass of a particle, but showed no deflection when passed through magnetic or electric fields. It carried no electrical charge. Chadwick had found the third subatomic particle. He named it the neutron, a particle that was slightly heavier than a proton, but electrically neutral. This discovery accounted for the missing mass. With the neutron, the physical weight of the atom finally aligned with experimental data. These three discoveries provide the framework for the modern atomic model used today. Every atom is built from these three primary components: the negative electron, the positive proton, and the neutral neutron. Protons and neutrons cluster together to form a dense central nucleus, which is surrounded by electrons in constant motion. This highly detailed, energetic internal system entirely replaced Dalton's completely outdated concept of the atom as just a simple, solid, inert sphere. The identification of these subatomic particles proved that the physical world is built upon a precise equilibrium of mass and charge.